So good morning and welcome to my presentation. So before starting, I would like to express my sincere thanks and gratitude to the team journal of electrical and computer engineering. So the title of presentation is Automated Lung Cancer, T-Stage Detection and Classification Using Improved Unit Model. So the agenda for today's presentation includes the introduction, the literature survey, the problem statement, objectives, methodology, research findings, finally the results and discussions and the references. Lung cancer. So cancer is an abnormal growth of cells. So where the cells are growing in an abnormal way. And finally, an uncontrollable form of growth results in the final stages and the deaths. So among the various types of cancers, lung cancer constitutes to around 25%, and the survival rate of the lung cancer can be improved, or the 5-year survival rate of the cancer patients can be improved to 17.17% when it can be diagnosed at the earlier stages. So the regular process or the steps in diagnosing the lung cancer includes the detection, classification, and staging. So the normal process or the method that is used for staging is called as TNM in short, that indicates the tumor, nodule, and metastasis. So coming to the lung cancer in India, so because I belong to the country of India, I would like to explain the statistics of the lung cancer in India. So around 72,000 number of cases annually records in India with lung cancers, out of which around 66,000 deaths are happening. So we can see the statistics around only 16% of the patient are diagnosed at the earlier stages. So if this diagnosis can be increased so that the lung cancer can be found out at the earlier stages, so definitely the survival rate can be increased. So the main cause or the reason for the lung cancer, which everyone is aware, is because of smoking. So other than this, we have some other causes like air pollutions, random exposures, passive smokers. All this may be the other causes. The treatments for the lung cancer includes the surgery, radiation therapy, chemotherapy, and targeted therapy. So these are the different treatments. So if a patient is affected with the lung cancer and he has to go for this treatments, then the early detection and classification and staging of lung cancer plays the main role. So that gave me the motivation to choose the topic. If the lung cancer could be staged to an appropriate stage at the earlier time, so the surgical cost can be reduced and the survival rate of the patients can also be increased. So generally the images or the process of identifying the lung cancer are, so the patient go for the CT imaging with the initial symptoms. Based on the CT images, if the tumor is identified, then biopsy process is carried out to identify to which particular stage the cancer belongs to, and appropriately the treatment is started. So here we can see the CT images plays a very important role in identifying the nodule. So because I have mentioned, I have used the TNM staging parameters to stage the lung cancer. So the TNM stands for tumor, nodule, and metastasis. So there are many editions. So now the latest edition is the 8th edition. So according to this, the various parameters using which we can assess the stage of the lung cancer are depicted here. So if there is no sign of a cancer, then that is identified as a T0. If the tumor is mildly invasive and we can see the size of the tumors that is in between lesser than 1 centimeter can be identified as a T1A stage. If the size of the tumor is between 1 to 2, it is T1B. So similarly, we have, based on the size of the tumors, the stage of the lung cancer can be classified into appropriate T stage. So the literature review is conducted to identify what are the existing methods to identify the T stage of lung cancer. So various reputed journal articles are considered to perform the literature review. So here is a summary. So how or what are the different techniques available for identifying the T stage of a lung cancer? So coming to the first article, the Targenti et al., the other authors, titled an article Detection of Lung Cancer Stages on Computer Tomography Image using Laplacian filter and marker-controlled watershed segmentation techniques. So the methodology what these authors have implemented is median filters, contrast enhancement, morphological operation, flood filling, outlining, marker control, watershed segmentation. They have used various parameters to assess or classify the lung cancer stage to an appropriate stage. So here we can see all the techniques or the methods that are used here are an image processing techniques where they will be playing around the pixels and it will be assessed with the individual or single slides. So when we want to assess the T stage with a single slide, it is obviously a time consuming process. And one more thing, we cannot assure that the cancer can be in a one slide of a CC. It can be prolonged or it can be um, maybe available in the different slides. So based on the one slide, we cannot come to a conclusion that the cancer belongs to a particular stage. So that is a key factor what I could able to identify in this. So coming to the second article. So Kashinathan and other authors so implemented a cloud-based tumor detection and stage classification. So here, as the name indicates, the author have used the cloud-based implementation where due to the huge data sets or the available platforms, they have used a cloud to implement this detection and classification. So the model they have used is the hybrid model for PET or CT images, a cloud-based tumor detection and stage classifier with an active counter model and a multi-layer convolution neural networks. So here the authors have combined the image processing techniques and the deep learning neural networks. So counter model is where placing a seed point in the image and it will extend its boundary to segment the nodules. And finally, they have trained the neural networks with the convolution neural networks. So the key factors of this particular article is they have a limited data set for testing and the larger data sets effectiveness is unknown. So coming to the next article, Koi J implemented an work with the title A Cascaded Neural Network for Staging in Non-Small Cell Lung Cancer using Pre-Treatment CT Images. So the techniques they have implemented is cascaded deep learning model where they could able to sequentially arrange the neural networks one after the other. The input of the one model is taken as output of the another model. And autoencoders and convolution neural networks are the other techniques which they have implemented to identify the stage of the lung cancer. The various parameters, again, they have used to justify the work. And the key factor we can see here is differentiate accuracies on different data sets requires large and diverse data sets. So they have converged to a minimal set. So coming to the next article, the Kavita MS and the other authors implemented an efficient classification model for cancer stage diagnosis in CT lung images using FCM and SBM. So here we can see the authors have implemented the techniques using the data mining techniques like SVM classifiers or the fuzzy C-means using the various filters to enhance the images. So here also the drawback is it is applicable for a specific image processing and data mining techniques. So today with the evolution of the deep learning models, I think it's better to go for the neural network models. And the last work here, Jackie Morsky, so implemented a work with the title using double convolution neural network for lung cancer stage detection. And the techniques they have used is a convolution neural network with the double deep neural network model with maximum pooling. So the key factor of this particular article can be it requires or they have implemented the work with the prolonged training over 100 epochs. So with the standard CDNN, the convolution deep neural network. So this model could able to obtain low accuracy. So based on this literature review, so the various gaps that was identified includes the existing method often lack accuracy in lung cancer stage detection, because as more number of images and patients are coming into picture, I think the model can be trained with more number of images and the accuracy can be increased. Accuracy plays a very important role in cancer detection, even if one wrong result may result in a wrong diagnosis. So accuracy definitely matters. So our model concentrates to improve the accuracy. So coming to the second one, the current method used for generating the segmentation marks involves a manual or a semi-automated process, so which are generally time-consuming and error-prone. So the third research gap is imbalanced data. So for example, when we try to train the model, in one particular stage, the number of images may be less. In another particular stage, the number of images may be more. So this imbalance may not result in accurate T-stage detection. So many prior models were validated using a small data sets. So here we have taken care that the model is trained with a large number of data sets. So some of the models has been trained for a prolonged epochs, so more than 100. So which is definitely with the deep neural networks training models, even a one epoch may be taking around 5 to 10 minutes. So 100 epochs and more than 100 epochs may even takes half a day or more. And the complexity, expensiveness, and time consuming is another factor. So we try to implement or fine tune the model so that within the limited number of epochs, the model could be able to train accurately. So definitely there is a need for an automated end-to-end solution that can handle the entire workflow from image acquisition to staging without extensive manual intervention. So all these gaps are taken into consideration to develop our model. So the problem statements. So the main objective was to increase the accuracy, effectively identify the stage of the lung cancer, for which we have proposed a modified or improved unit model with an added advanced residual network to enhance the segmentation accuracy. And automated mask generation process is carried out. A feature-based classification is implemented, and it is validated on a large data set. So coming to the proposed technique, so here we can see the flow. So the input CT images, which are pre-processed to reduce the noise and enhance the quality of the images. So because we need to identify even the smaller nodules in the CT images, so the contrast or the image enhancement and the noise reduction process is carried out in the pre-processing stage. So I'll be explaining all the steps in details in the coming slides. The overview here is the main objective of this particular proposed model is to generate a mask. So from this generated mask, following these steps, so initially there will be a thresholding operation. From the thresholding operation, there will be a morphological border removal, finding two largest components, again applying the threshold, finding the largest components, region filling, and finally the mask will be generated. This mask is given as an input for the image augmentation process along with the pre-processed image. So image augmentation tries to improve the quantity of the images. And finally, the segmented mask or the nodule mask that is generated and the pre-processed image along with the augmented altogether is given as an input for the improved unit model, and successfully could able to segment the nodule and finally detect at what particular stage the lung cancer is, and the performance of the model is evaluated with various metrics. So coming to the first stage, so as I mentioned, I will be explaining the proposed model in a detailed phase. So pre-processing. So pre-processing plays a very important role in the noise removal process. So noise removal process and enhancing the quality of the images definitely increases the accuracy of the lung cancer stage detection. To implement this, we have used a contrast limited adaptive histogram equalization. So this is the extended version of the histogram equalization. So the main objective of choosing this advanced technique is, so it operates on a smaller regions in a form of a tile. So we are not going to consider the entire image as one input and perform the histogram equalization where the graph is converted to a bell curve with a number of intensities and number of such intensities in the y-axis. So here, the entire image will be taken or considered in a form of a tiled segments. So starting from a top leftmost corner and sliding the tile each time towards the left side and below, so that a smaller segment of the image is taken and it is enhanced. So based on the smaller tile portion, an adaptive equalization will be performed and histogram graph will be plotted, and that particular segment will be enhanced first and later the next tile. And this process is continued for the entire images. So this will give us a better quality of the image, thereby reducing the noise. So we can see here, these are the outputs of the enhanced images. So we have compared the original images, the normal histogram equalization, the grayscale image that is converted, and finally CLAHE, that is contrast limited adaptive histogram equalization. So by looking at our naked eyes itself, we can see the quality of the enhanced image when compared to the original image. So this is a normal histogram equalization where it is becoming still more blur, but the outer regions we can see are getting enhanced. But we need the additional or more information in this particular region. So grayscale will not able to detect the nodules if it is present, or the smaller nodules that is present here. But here we can see this may be, but here we don't have a nodules here. But this may be the blood vessels that after enhancing can be seen very clearly. If there is a very small nodule that can also be enhanced and visible in this particular enhancement process. So coming to the mask generation process, which is a novel work that we have implemented here. So the mask generation process for the unit segmentation plays a very important role. So generally, the process that is carried out nowadays is a manual or a semi-manual process. So generally, which is a time-consuming as well as error-prone. So there are different techniques of mask generations available, like region of interest, where we want to give the region of interest in which we need to segment a particular part. But the drawback is we need to give the additional information like the coordinates information X, Y, and the number of pixels in the resolution M cross N. So coming to the next method of generating the mask, the counter method. So this will better generate a mask in a better efficient or accurate way, but placing the seed point is a matter. So this is not a fully automated process. Initially placing the seed point within the segmented or the region we want to segment plays a main role. So it is not at all an automated process. So to overcome this existing mask generation process, we have implemented a fully automated technique so that generates the mask effectively. So these are the steps that is carried out to generate the mask. So initially we can see. Okay. So initially we can see the input CT images are given as input to the model. So that contains all the information like lung regions, the ribs, the anatomical structures like maybe the bones or any other regions. So this is given as an input. So we are considering the actual view of a CT images. So that is like exactly cut the body at this particular part. So for the CT images, the first step that is applied is a thresholding. So where we convert all the pixels to two intensity values. So to black and white. In general, we can call this process of converting the image to a black and white image. So this will convert our entire grayscale image to a black and white image. A particular threshold point or a value is chosen. All the pixel value above the threshold value is set to white, and all the pixel value below the threshold point is set to black. Thereby, we can able to convert the given image into a binary image. So once the threshold process is done, so the next step carried out is a morphological process like dilation and erosion. So this helps to improve the segmentation by closing the small gaps, because once we have applied the thresholding, there may be a chances that smaller or a minute information may be lost. So to fill this edges with the smaller gaps, so we use the morphological process. So for this, we have used the disk with a radius of 2. So that has successfully given us the exact region to be segmented. Either it can be a lung or the nodule without losing its information. So as we have seen, the input CT images will contain many informations like the bones or the muscles, all other information. So the border removal process will be considered to include only the lung region. So to be specific, the lung region and the outer part of the lung region, all other additional information will be removed. So, border removal process will be removing the outer regions of the lung CT images. So coming to the lung mask generation. So from the border remote process, the two or first two connected components will be identified. So I will be showing that in the output. So this first two connected components will be the biggest part of the CT images that constitutes or contributes to the lung region. So once we could able to identify the two lung regions, so that gives us the segmented lung region. But we are still more concentrating to generate the mask in and around the nodule region, not only the lung region we are segmenting. So inside the lung region, we are going to concentrate on the nodule region. So this is our first phase of our mask generation. Again, a sequence of steps is carried out. So from the segmented lung region, once again, we are targeting to apply the thresholding operation, where again the image is converted to a black and white, but this time the image will consist of only the segments of lungs and the inner regions. So again, the region filling operation. So again, we identify the two smaller, the one connected component. I'm sorry for that. So the first or the biggest connected components, so that will be considered as a nodule part. So once this is identified, all other gaps or the holes are filled with the region filling process. So once it is done, finally the region in and around the lung nodule is identified, and this will be considered as a generated mask. So here we can see the set of outputs that is obtained after the each steps what I have explained. So this is the whole slided or input CT images. So this is converted to a threshold. After applying the thresholding operation, the input CT images is converted to a binary image. So this is given to a morphological operation where the smaller gaps around this will be removed in the border removal phase, and this unwanted regions will also be eliminated. So here we can see now we have only the lung regions and the region around the lungs, which may be exactly the human body. All other things are eliminated. So from this, again, we are going to remove the border so that we consider only the two parts of the lung regions, identifying the two connected components. From these two connected components, we are going to fill all the holes within this particular regions. So we got a mask of the lung region. This is imposed with the original CT images, so that I'm going to retrieve only the segmented lung region from the input CT images. So as a matter of fact, this itself can be given as an input for the unit, but still more we are concentrating to get the outer regions of the nodules. So from this lung region, again, thresholding operation is carried out. So it's converted into a black and white binary images. From this, the biggest connected component is identified. So the biggest connected component is identified. So this helps us as a mask to segment the region around the lung regions. So when we superimpose with the original CT image or with the segmented lung region, we can able to obtain the in and around region along with the nodules. So this is what is a mask generated. So from this mask generated, we next concentrate on the data augmentation process. So once the image pre-processing and the mask generation stage is over, we concentrate on data augmentation process. So data augmentation process, as I mentioned earlier, in the research gap identified. So some of the stages will have less number of data. Some of the classes of the stage will have the higher number of data. To overcome this, we have used the data augmentation process. So data augmentation is generally increasing the quantity of the images by rotating, inverting, shifting, zooming, and other operations. So the general techniques are these things, but we have implemented the extended Mobius augmentation technique, which is an extended version of a Mobius augmentation technique, which generally uses 3 points. But here we have used 4-point Mobius augmentation techniques, which will include all these operations in it. So the difference between the normal augmentation and the Mobius augmentation technique we can see here. In the normal augmentation process, we need to mention what are the different augmentation that needs to be carried out with the various parameters and values and the ratios and different other parameters. Whereas coming to the Mobius augmentation techniques, assume this is an image. I'm going to choose of 8 points. So x1 to x4 and y1 to y4. The traditional Mobius augmentation technique uses 3 points, but we have implemented a novel process here to select 4 points. So here we can see by moving these points, x1. One second, sorry. Yes, x1 to y1, x2 to y2, x3 to y3, and x4 to y4. So like this, we are going to generate the points within the images so that we can able to move and produce this effect of shifting or inversion or rotation or zooming or shrinking or whatever the process is. So coming to the mathematical process of calculating the transformation. The Mobius transformation is given by a complex function, my plus n whole divided by py plus q, where m, n, p, and q are the constant values. So we need to identify the value of m and pq in such a way that the product of mq minus nq should not be equal to 0. But rather than specifying this values of m and pq directly, so we have used a complex function or a Laplacian transformation to find out the value of m and pq. For this, as I mentioned earlier, so we are choosing the points x1, x2, x3, x4, y1, y2, y3, y4. Based on these points, we calculate the value of m, n, p, and q using the Laplacian expansion with the linear algebra determinant evaluation technique. So from this identified value of m and pq, so we could able to identify the transformation of the points x and y. So thereby achieving all the operations of augmentation and thus increasing the quantity of the images. So these are the outputs or the sample outputs of the augmentation. So these are the inputs. This is inverted left, and this is again rotated right. So this is an appropriate mask that is generated, which is also augmented. So this images with the augmented original CT images and the mask will be given as the input for our modified unit model. So unit is a type of a convolution neural network, so which is generally designed for a segmentation. But when we apply this unit segmentation model directly on the CT images, maybe it will not exactly segment the lung nodules effectively. That is the reason we have generated a mask in the previous step. And the unit model that is used here is not the traditional one. So we have improved or modified the unit model by adding the advanced residual network. So we have named it as ARESNET. So the model is incorporated. So this addition of ARESNET layer helps in extracting the essential features more effectively, improving the segmentation accuracy by focusing on vital features and minimizing the influence of less critical ones. Also, this layer, that is the ARESNET, consists of the batch normalization process. So this steps stabilizes and accelerate the training process, improving the model's performance and convergence speed. So this is the improved unit model. So as we can see here, after every layers or a group of layers with the convolution and max pooling, so we are adding the ARESNET. So ARESNET model is projected here. So we are taking care of the batch normalization with the ReLU activation function. So if this is the input CT images along with the given mask, so finally there will be a segmented output that will be generated. So this is a screenshot or the outputs of the modified unit model. So this is the input CT images. This is the CLAHE enhanced image. And this is the generated mask with our image processing technique. And finally, with the modified or improved unit model, this is the segment nodule. Sorry, this is the segmented nodule. So from the given input CT images, we could able to exactly or appropriately segment the given nodule as shown in the image here. So coming to the performance evaluations, or the other techniques of evaluating the model. So here we can see initially we have trained the model without fine-tuning it, without any augmentation process or pre-processing or adding the ARESNet to the unit model. So we can see a very huge gap between the training and validation. So it is the problem of overfitting. So once the model is fine-tuned with this augmentation, image pre-processing, and a modified unit model, we can see the accuracy of the validation has drastically increased. So it has reached around 94%, and the loss also could be able to reduce below 0. And the number of epochs we concentrated here is 50, but this is for a confirmation. But the model, when it is trained again, could able to achieve the accuracy, a good accuracy of training for testing and validation within 30 epochs. So coming to the nodule segmentation, we have not evaluated the the model only with the performance evaluation of staging, but also how effectively the nodule is segmented. So we have choose the input image and the segmented image as an input to verify how effectively the nodule is segmented, for which we have used the parameters like average, mean, intersection over union jacket, and dissimilarity coefficient, jacket distance, and head of distance. So the higher value of MIOV, IOU jacket and DSC indicates that the model has a very good segmentation, and a less value of jacket distance and host of distance indicates that the model is performing better. So our pink color line or the bar indicates the proposed model, which gives us the better segmentation when compared to the other existing models like RCNN or FCN or the traditional unit or unit model with the general adversarial neural network. So our model could be able to segment the nodules more effectively. So this is the confusion matrix of the staging. So once the model could able to segment the nodules based on the size of the nodules, we could able to use a fuzzy logic to classify this nodules to an appropriate stage. So as we can see from the confusion matrix, so these are the numbers that could be correctly classified to an appropriate stage. So these are the true labels and this is the predicted value. And there are few errors or non-appropriate values. So this 2, 3, 4, 5, 4, 2, 1, and this 4 and 4 and 3. So these are the nodules which are misclassified or classified wrong, because we can see a nodule that should be predicted as T1C is predicted as T1B. So this may happen or T2A. So this is what is the smaller errors that happens due to the size, because some nodules may range its size in between T1A and T1B. In such cases, definitely the classification goes wrong. So, but still we can see our model could be able to achieve a very good classification. The diagonal numbers are really huge. So coming to the performance metrics based on the confusion matrix, we could be able to calculate the accuracy, the precision, the recall, and the F1 score for the various stages. And these are the values that are obtained. And the overall accuracy of the proposed model was around 94%. So when compared to the existing techniques or the existing models, so the proposed model, when compared to the Laplacian fuzzy C means SVM, the data mining techniques, the median filter and multi-class SVM, the deep convolution neural networks or 3D convolution neural networks, or only traditional unit models, what we have discussed in the literature review, our model could be able to obtain a better accuracy or a higher accuracy than the existing models. So as we can see, the fuzzy C means with the SVM could be able to achieve an accuracy of around 92.5, but the proposed model could cross 94 with the proposed model. So coming to the conclusion, so this paper proposed an automated technique for the detection and staging of lung tumor. So that combines an improved unit model with an advanced residual neural network. So the model implemented CLAHE, advanced technique of histogram equalization and adaptive technique to enhance the image in a tile form. An extended Mobius augmentation process is used to increase and balance the data sets in all the stages. So this is one more novelty that we could be able to implement. So the model could able to achieve an overall accuracy of 90% and demonstrating its superior performance than the existing techniques. The finding demonstrate that the recommended approach offers a stable and efficient means of staging lung cancer, significantly improving the precision and consistency of early stage detection and the diagnosis of the treatment planning process. Finally, the model could able to offer a non-invasive, low-cost solution that can be developed for a wider application in medical imaging. The proposed method would increase the accuracy of the lung cancer staging, which would help the patients and advance in the field of medical oncology. So in the further studies, the researchers could concentrate on increasing still more accuracy with the wider data sets and the real-time data implementation. And these are the various references what I have used in my article. So thank you. Thank you for listening. So hope I have covered all the points that is published in the paper. Thank you again. Thank you one and all.